Okay, so last lesson is 9-7, and copied for you in your note packet are the concept summary. So don't forget that linear functions are going to make a nice straight line, either traveling up or traveling down, and that your equation will be y equal mx plus b. You know, something in that format. All right. Quadratic now is going to make a parabola, either opening up or opening down. That's what it looks like on the graph. And you're looking for the highest degree of your function to be a 2, okay? You want that exponent to be 2. And then exponential, this is the one that kind of gets confused, okay? Exponential also has an exponent on it, right? But the exponent is an x, not a 2. All right, it's an x. And so the difference on the graph here is it either starts real low and then goes up really fast. Remember, exponential can decay though as well, so it can start really high and then like zoom down really fast as well. Okay. All right. So here's our first set of things that we need to know when comparing them. So sometimes they'll just give you a set of ordered pairs. And you got to know in your head what the graph looks like to decide what kind of function is this function. So you can just do a quick sketch of a graph. So A, how big does this graph actually have to be? What's the highest number?
3.
A 3, right? So you can work smart, not hard. Do a 3 by 3 graph or even a 4 by 4 if you want to have a little room. Okay? You don't have to do a 10 by 10 graph if there is not that many points and if they're not asking you to make further predictions. So I'm just going to do a 4 by to give a little bit of extra room. And then I'm going to graph it. So I'm going to go right 1 up 3, 0, 0, left 3 up 3, 1, 2, 3. Negative 1, negative 1, and then negative 2 and 0. So if I put all these dots on the graph, mine's a little hard to see. I should have probably done the dots in a different color. But if I were to connect them, the ones that I've got here, what does it appear to be here? What kind of graph does that look like? Go, Xavier.
Quadratic.
Yeah, this is a quadratic graph. It makes that nice parabola there, and even just sketching it out, you can see, it's going to make that U shape. It's a quadratic. Okay, next one. What's the highest amount I have to go to on B? 4. So again, you can make it one higher and make it a 5 by 5 just to get a good picture, or you don't have to because there's no extra predictions. It's not saying, and then what's going to happen next, you know? It's literally just asking you to graph it. So 0, 2, negative 1, 4, 1, 1, and 2, 0.5, and that one's kind of hard to put in. But when you then connect them, what kind of shape graph is that going to end up making? Exponential, that's right. It's making that curved shape. So this is the exponential, which means probably the last one's going to be linear since we're comparing them. But let's just graph it just to show us how we do it. What's the biggest number this one goes to? I disagree. 3. I'm going to go by 4s just because I have that enough space there. 2, 3, 4. All right, negative 1 and negative 2. 0, negative 1. 1, 0. And then 3. Oops. 1, 2, 3, and then 2. Okay, so, oops, I made my first point wrong. Nobody said anything. Negative 1, negative 2. Ooh, I'm going crazy. All right. And does it make linear or no?
Yes.
Yeah, it totally does.
Okay.
Boop. Sorry about that, but this is linear. And so that's pretty easy. Sometimes, you know, we get really used to using our graphing calculators, but sometimes you have no choice. Just do it by hand, make a little sketch of a graph, and especially if that's the only information you've got. Now, graphing is pretty easy, and the question is, how do you tell from a table, okay? So I copied 3 tables for you, okay? So take a look. This is table 1, 2, and 3. And it also already showing you the differences. So one of these graphs is quadratic, one of them is exponential, and one of them is linear. Which is which? What do you think you know? Which one is quadratic, which one's exponential, and which one is linear? Go ahead, Xavier, what do you think?
I think that the last one is quadratic.
You're right, the last one is quadratic. And I'm going to explain to you guys in a little bit. What do you think of the first 2? The first one is linear. That's right. Okay, so linear, exponential, and quadratic. Now, let's make sure we point out what makes them this. So linear versus exponential. What is the major difference between those 2? Cody, go ahead. Yes. Yep. That is exactly right. So something to note is we're adding by 1 and adding by 3 in this example, but we could also subtract, right? So linear, you're going to have a common difference here. Like it's going to be common here and here. You're going to either add or subtract by the same amount each time. And that's going to end up, that's your slope, right? Your change here divided by your change here is your slope, okay? By same amount each time. And that difference is, so remember, your change in y over your change in x is your slope. y2 minus y1 over x2 minus x1, okay? In your exponential, this is multiplying by 2 each time, but what else can exponential do? Divide by the same amount each time. Or multiply by a fraction, right? So it's really multiply or divide by the same amount each time. So remember that dividing is the same as multiplying by a fraction though. So like when you're doing the function, we use a fraction. We don't use division. And then the quadratic, which we haven't really discovered yet, but there's something called a first difference here, right? So the difference between 1 and -1 is -2. And then the difference between -1 and 1 is +2. 1 and 7 is 6, and then 7 to 17 is 10. But if you go a second time, there's a second difference. The difference between the second numbers is always 4, okay? So here, your second difference will add or subtract by the same amount each time. Okay, and so that's the main part of a quadratic, is it does not appear as though there's a common difference at first, but then you check the second difference and you're like, oh, it is the same every time on the second difference. And also, there will be a mirroring effect that happens here, right? So can you see right now, what's the vertex of the quadratic function here? It's going to make a mirror effect, right? I can see the vertex right now. What is it, Elvin? It's 0, -1. See it right here? Okay, so 0, -1, because this is going to, so what's -2, the value going to be for y? 7, right? What's -3 going to be? 17. It's going to mirror up each time. Okay, cool. So that's the main idea. Now let's put it into practice. Let me show you, okay? All right, so here's a good example of this type of problem. It'll say which type of function best models the data use, differences or ratios, okay? So all you have to do is take a look at what we're doing on each side. So for A, our x value, what's happening here? Every time it is, for x value, what is it doing? Adding by 1 each time, right? So every time, and that's super important that we can see that. All right, what's our y value doing? It's subtracting by 4 each time.
So it's linear.
So it's linear, that's right. So this guy is linear. Those are the easiest to spot if they are in fact like going in a pattern on both sides. Sometimes it's harder if they're all over, if they don't put them in order, or they don't do, if your x values are not doing a pattern, then your y values won't either, no matter what. Okay, let's do this one. Our x values, are they going in a pattern? Yep, those are going up by 1 each time. Okay, great. What's happening to our y values each time here? 0, negative 0.25, negative 1, negative 2.25, negative 4. So the first one's minus 0.25. What's this one, though, next? Minus what? 0.75? Then what? What? 1.125? Oops. Minus what here now? 1.75? That's our first difference. Now let's see if there's a second difference here.
Oh, yeah.
Negative 0.5? What about here? Negative 0.5? What about here?
Quadratic.
So this one is quadratic. Because our second difference, right, was common. Good, good? Okay, one last one. So this one is what I think is the most challenging. Because it says, so right here it says the data at the right give the value of a used car over time. Which type of function best models the data? Write an equation to model the data. So at year 0, right, when you first buy the used car, it's worth $12,575. A year later, it is only worth $11,065, and so your value is depreciating each year. It's going down, right? But is it going down by the same amount each time? Let's find out. So this is going up, right, by 1 each time. And now what's happening here? Is there a common difference here? So 12,575 minus 11,065. What's the value going down by here? So minus 1,510. Okay, is this one the same?
No.
Okay, 11,065 minus 9,750.
Yeah.
Minus 1,350. 15. Thank you. Minus 1,315. So already we don't have a common difference here, right? But let's think about what's happening on a used car, right? Are we going to get a second common difference, do you think? Is this going to be a quadratic function where you get the parabola, where the used car goes down and then goes back up? Could be. So how do we check for exponential? That's the toughest one. How do we figure out if it's multiplying or dividing by the same amount each time?
We eliminate the yellow?
Nope. Here's what we do. We do something is we check for a common ratio. All right? And that's the question, okay? How you check for a common ratio is, if this is going up by the same amount each time, you divide by each one. So my first one that I would divide would be 11,065 divided by the one before it, 12,575. And we're going to round this, okay? So divide it and give me the decimal to the nearest hundredth. Okay? So then we're going to check the next one. So we'll take our next set, which would be 9,750, and we'll divide it by the one before it, 11,065. And we're going to divide that, and we're going to do to the nearest hundredth again. Same thing? Round to the same thing? Yep. Okay, and then we do the next one. 8,520 divided by 9,750. Rounded. $8.7 though this time, but we're rounding, right? Every time we're rounding. Okay, and then last but not least, 7,540 divided by 8,520. Round it. 0.88. So, if we're rounding, are we pretty close to having a common ratio?
Yeah.
The answer is yes. So if we're really close, then we can say, in fact, that this is exponential. Because we have that common ratio, okay? Now, how do we write an equation for this, okay? Remember that the exponential function, which is on our previous page, is y equals a, our initial value, times b to the x power, where b then is our rate, right? So in this case, what's our initial value of our car? Go ahead, Donovan. 12,575, and we're going to times that by, is our car appreciating or depreciating? So we know we're going to not put a 1 in front of this. We're going to leave it 0.88 because that was the most common. And then what else am I going to put on it? The x power. This is our exponential function. That is going to be our equation for that. Okay, cool. That is the lesson. All right. People at home, if you need questions, please feel free to email me. I'll get back to you as soon as possible.